Hi, in this video we will discuss the continuity which occurs only from one side, from left or right. You will see that this notion is a very natural notion while studying piecewise defined functions, and we will do some examples for this topic. Okay, so let me start with an example, something that we can do at this stage without any other knowledge from the topic. Well, we have a function, and the question has to check the continuity of the function, which is piecewise defined, and then, well, that's it. For x is bigger than or equal to 0, it's 1 over x squared plus 1. And for x is less than 0, this is 2x plus 2. So first thing to note is that on all x's for any x, which is a positive number bigger than 0, the function is 1 over x squared plus 1. Yeah, this is a rational function, which is a rational function. Well, rational functions, remember where the discontinuities of rational functions are, wherever the denominator is 0. Here, the x squared plus 1 cannot be equal to 0 for real x's, yes. So this is positive number add to 1 is going to be always bigger than equal to 1, so it cannot be 0. It means that it's a rational function that doesn't have any root in the denominator, and well, as a result is continuous on all positive numbers. Actually, it is continuous everywhere, but what I need is only this piece because the function is defined there. So that's first thing. So on x is bigger than 0, the function f is continuous. For x is less than 0, on the other hand, it is basically, well, it is polynomial. It is a polynomial. And well, polynomials are continuous everywhere, so that as a result f is continuous for all x less than 0. That's nice. So for all x is bigger than 0, it is continuous. For all x is less than 0, it's continuous. Now we have to check continuity at x equal to 0. And continuity at x equal to 0 means what? Means that we have to first check if the function is defined at 0 or not. F is defined. Why? Because you see, it says that as if x is 0, bigger than equal to 0 or 0, you use this formula. And while f at 0 is going to be 1 over 0 squared plus 1, which is just 1. But that's defined. How about limit of function? Limit of f of x as x goes to 0. Well, we remember from the old days that when you have a piecewise defined function and the point at which the domain is separated, bigger than, less than, those points, when you're studying limit of function at those points, the best way is to separate these ones to one-sided limits. So x goes to 0 plus limit of f of x, x goes to 0 minus. For x going to 0 plus means that we are using only values bigger than 0. So the function would be of this form. For the other one, function will be just this one. Now, well, these are just find the limit, which is just plug in basically those ones, because we can apply the quotient law here, and that gives us 1. But here is polynomial again. A direct substitution is what we have. So what did we get here? For left limit is 2, right limit is 1. As a result, well, since these two limits are not equal, we can say that the function doesn't have limit at 0. Yes, so the limit does not exist. Well, then the second condition failed, and then we conclude that f is not continuous at x equal to 0. So what we did find is that f is continuous for all x is bigger than 0, for all x is less than 0, but at 0 it is not continuous. So as a summary, f is continuous at all real numbers but x equal to 0. So that's a very typical example you will see us doing. But one thing that comes out of this example is that although the definition is always the same, function is defined, the limit exists, and these are equal. But in the case of the piecewise defined functions, maybe we have to do a little bit, always try to do this thing. So in the case of separating point of domain of a piecewise defined function or functions, what we do is that, well, we not only we check first of all limit, the function is defined, and it is the value is, well, we have the value. We also need to check the limit, but limit at those points, the best way to approach those points is from the right and then from the left separately, and then set them equal to each other. So we have to see, so then in other words, we check f is defined at a. I will do the step 2. Well, step 2 will have 2 steps. Limit of f of x as x goes to a minus exists, and limit of f of x as x goes to a plus exists. Then the third step is that, well, the fourth step, or all the above numbers are equal. Well, let's do one example, the different type of example for this one. The example we did above shows everything, but let me do this example too. So example, find value of a for which f of x equals to a x plus 2 for all x is bigger than equal to negative 2, and x plus 1 for all x is less than negative 2 is continuous at all real numbers. So we are going to find value of a for which this function will turn out to be continuous everywhere. So again, as we had before, you have to note that each formula for itself may have its own discontinuities. But in this case, so note that both formulas, I mean ax plus 2 and x plus 1 are continuous everywhere. Well, continuous everywhere. Why? Because these are polynomials. Doesn't matter what is a. Whatever you put for a, it's going to be a polynomial. Polynomial are continuous everywhere. But these guys on this function deal they only give values for x is bigger than equal to -2 and less than equal to -2. So this means that as a result, f of x is continuous for all x's bigger than -2 and less than -2. Why didn't I include the equality here? Because you see the equality is there. Why didn't I say for all x is bigger than equal to -2? Because, well, continuity is not just one point. It is related to values of the function around that point too. Here, this formula has only one side. So this cannot by itself give information about the whole continuity. It just can do one side. Yes, that's why we exclude that -2. Well, and we have to study -2 separately. At x equal to -2, f at -2 is defined, well, and it is given by a times -2 plus 2. And this is separating point of the function, so we have to go from the right. Let me do first this for the -2. So this will be for x is bigger than -2. I can use ax plus 2 as x goes to -2. And this gives us -2a plus 2 as the value of the function. And for the left one, we have limit of x plus 1 as x goes to -2. This is -2 plus 1, which is -1. Now we have to set all these numbers equal to each other, left, right, and the function itself. But these two, the function, the value of the function and the right limit, these are already same thing. So, well, let me just write this. This needs to be equal to that, equals to -1. Well, these two are already equal, so we have to solve this equation. What this gives us is an equation in terms of a's. That's something you have to always keep in mind, that we are basically trying to get an equation and then solve it for a, and that is how we get the value of a. If a is 3/2, the function is going to be continuous at -2. Well, always when you work with one-sided limits, when you work with piecewise defined functions, you always try to use one-sided limits and so on. The second limit about this examples is that, well, let me just write this remark too. Remember that the definition of the limit, the continuity definition, definition, which is, well, what is it? Limit of function x goes to a equals to f of a can be somehow, let me say, generalize it, but it's not that word is not correct. But what I mean is that I can modify this, or it can be modified to define one-sided continuity. What I mean by this is that, okay, we can say, so this is definition, f is continuous from the right at x equal to a if, well, if and only if, that's the definition, limit of function as x goes to a, not the whole thing, but only as x goes to a plus is equal to f of a. So it means that f is defined, left limit, right limit is given, right limit exists, and we are not forcing both right and left limit to be equal and equal to the function value of the function. We are just forcing that f of a and lim as x goes to a plus are equal. That's what it means, continuous from the right. While similarly f is continuous from the left at x equal to a if limit of function only when a goes to a, x goes to a minus, approaches to a minus, is equal to f. So that kind of gives us one-sided continuity. But the important point that this one-sided continuity is used is that when you want to define a function is continuous on an interval. So this is the final definition for us. Definition. F is defined, okay, let f be defined on the interval AB, closed AB. We say f is continuous on AB, on the interval, not at a point, on the whole interval, if this happens. First, if f is continuous at all points of the interval, open interval AB. Yes, continuity makes sense only when you can approach to A from both sides. But AB, we can only approach them only from one side. So being continuous on a closed interval means that it is continuous on the open interval, and f is continuous from the left at B, and f is continuous from the right at A. So if you consider the graph of the function, So graph is continuous here up to this point, up to B. And then at B, it is continuous from the left. At A is continuous from the right. Yeah. For example, you see this example. Let us just go up there here. The first example we have here. This guy here. What we showed is that this guy is continuous from the right at 1. So that previous, the original example, so f of x 1 over x squared plus 1 for x is bigger than equal to -2 and x is less than 2. The example that we had is continuous on, was it negative, I believe. Oh, it was just 0, sorry, not the -2. Yeah, at 0, not -2, okay? So it is continuous. It wasn't continuous at 0, but it was continuous only from the right, so it will be continuous on 0, and well, you go up any point you like. Yeah. Or f of x equals to root x. This is only defined for values x is bigger than 0, and at 0 is also continuous from the right, and that's said the continuous interval is from 0 to plus infinity. Well, this was about the one-sided continuity, or whenever you study the continuity of functions with for functions which are piecewise defined, and we saw that we have to bring in the right limit and left limit in those examples.